How fast am I going part 2? Today we're going to continue our learning target and I can evaluate the average rate of change using smaller intervals. Again, you want to make sure you have binder paper and pencil, title up your notes, make sure you put your date on it, draw all diagrams and please show all your work. Here are the questions that you want to focus on for today's quiz. How is a difference quotient useful? What is the average rate of change for the function d of t equals 10t squared between t equals 3 to t equals 3 plus h? D of t equals 10t squared where d is distance and t is time. Calculate the average velocity from t equals 3.999 to t equals 4. And lastly, you're going to create two questions or two specific understandings you have from creating an equation to represent the average rate of change. So keep these in mind as we go through the video. So we're going to go ahead and jump into problem 7-95. Let's go ahead and read this problem and then we're going to tackle all of this. So in the previous problem, h changed while t equals 5 did not. This causes repetition in your average velocity calculations. To simplify this process, complete the parts below to calculate the average velocity of the same car from t equals 5 to t equals 5 plus h. So problem 7-95 is in reference to problem 7-94, which was in the previous video. From when they're talking about the repetition and the average velocity calculations, they're talking about this. So for example, when we had h was 0.5, we had to do a whole setup of creating 2 points, plugging in, and then doing some math each and every time. This is actually very repetitive. So what we're going to be doing is creating an equation that represents all average rate of change for any h for t equals 5 seconds, because that's the point that we're concerned with here. All right, so how do we do that? Well, first, because we're still using the same distance formula, it says from the same car, let's just make sure we have that here. And again, this is from 7-94. This is the car that's traveling where d is distance and t was time in seconds. And we're taking a look at when t was 5 seconds in that previous video. The next thing I'm going to do is go back. This right here, I'm going to simplify this image. So first off, you should be sketching this in your notes. But before that, this right here, 5 plus h minus 5, well, that's just h. I want to simplify things. Let's just call this horizontal distance right here h. This right here, I don't want to complicate things, so let's not even consider it. Go ahead and draw this picture right here, this diagram for what we're looking at. So the 2 points in question that we're going to be looking at is 5, 250, and then 5 plus h, 10, parentheses, 5 plus h squared, end parentheses. Now, this is a great visual because it's showing you that when the time is 5 seconds, you get 250 feet. And then here, if you move over some h amount, you're going to have 5 plus h. You take 5 plus h and you plug it into the function to get your output. Okay, so this is a great visual. Then it says write an expression for the average velocity of the car over the interval between t equals 5 seconds and 5 plus h seconds. Simplify your result as much as possible and compare your result with your team. Well, your team will be here with me. So let's do this. So our 2 points are 5, 250 and 5 plus h, 10, parentheses, 5 plus h squared, close parentheses. So again, let me remind you all where we got these 2 points. They come from taking this first one when t equals 5 and plugging it into our function for t. Remember in our previous video, we did 5 squared, 25, times 10, 250. The second point right here we got by plugging in 5 plus h in for t. See, if we plug in 5 plus h, that's your x value, you get this output. See, instead of t, we put in 5 plus h. So that's where this came from. All right, now we're going to go ahead and, because we don't have any h values, notice we don't have any h here, we're going to try to create an expression for the average rate of change with h in our answer. At the end of this, we'll see the usefulness of it. So let's see. All right, so now we have our 2 points. I'm going to go ahead and try to simplify this part. Take a look. And then, by the way, this right here is going to be the difference quotient. Anytime you have like a value and then plus h as your input like this, think of this as like x plus h. What this is, and then you calculate the slope, is you're calculating the difference quotient. And let me go ahead and answer up that first question is, how is the difference quotient useful? So the difference quotient right here is going to be useful because we're going to get an expression that involves h, and we'll be able to manipulate and change h without creating a repetition of calculations. Please make sure you write that down. You could go back in the video and just have me repeat that. So that is why the difference quotient is important. This right here, these 2 points, we're going to be setting up a difference quotient right now. But before that, let's go ahead and simplify this part to this. Notice how everything stayed the same except for this part in the parentheses. 5 plus h squared became this. Now if you forgot, like, how did we go from here to here? Let me just quickly go over how I did that by just switching the slide. Let's give this time to load. To here. So how we did that is to remember 5 plus h squared is actually the same thing as 5 plus h times 5 plus h exclamations. How you multiply this out is you could either use rainbow method or box method. Rainbow method is you basically go like this. See this? Where the arrows are going, 5 times h is 5h, h times 5 is 5h, h times h squared. Then at the end we combine like terms, 5h plus 5h, that's 10h. And that's how I got that answer. Or you could use box method as well. 5 plus h here, 5 plus h. So h times 5, 5h. h times, or I think I do 5 times 5 next here. Oh, never mind. H times h squared. Then I think I do 5 times 5, 25. And then h times 5 lastly is 5h. What's cool about the box method is usually these diagonals are the like terms and they add up. And I get this, which is the same answer. So that's where that came from, in case you were curious or in case you needed a little refresher on that. Now let me go back to this one. Let's go back to where we left off. Okay. Great, so we already talked about how we went from here to here. Now here's my next step. In this next step, all I did is I took that 10 and I distributed it in right here. And that's how I got 250 plus 100h plus 10h squared. Again, I distributed that 10 in here. Okay, great. So it looks like I simplified this as much as possible. These are simplified. Great. Now we're going to go ahead and create the average velocity equation, or the average rate of change equation. y2 minus y1 all over x2 minus x1. See, I just did my y2 minus y1 and then my x2 minus x1 right here. What's nice about this at this point is that things are going to cancel out. 250 minus 250, we could already just, 250 minus 250 is 0. Then we have 5 minus 5, that cancels out. So we got a nicer equation. The next part that we're going to do to simplify this even further is going to be, you notice this h right here and this h squared right here. We're going to pull out a common factor of h. I'm just going to factor out the h. Think of it like backwards distribution. And if you're still like wrapping your mind around this, if I was to multiply this h back in like this, I would get 100h plus 10h squared. But think of it as like I pulled out one h, and this is what I'm left with inside the parentheses, left over with. So that's why and how that happened. Now we have h here and h here. We could go ahead and cancel out these h's to get 100 plus 10h. That's really, really nicer than this that we had right here. All right, so, well, what is this? Well, this represents the average rate of change. So this right here, the units are feet per second. So let me bring this up again. So remember when we did our whole calculation when h was 0.5 and we got 105 feet squared? Well, when h is 0.5, all we have to do is substitute 0.5 for h right here. 100 plus 10 times 0.5. So 10 times 0.5, that's half of 10. That's going to be 5. So then 100 plus 5, check, 105. Here, if I plugged in 0.1 for h right here into this much simpler equation, I'm going to get 100 plus 1, because 0.1 times 10 is just 1, and I get 101 feet per second. So notice that this right here gives me a much easier equation to plug in for any h I want, instead of doing these repetitive long calculations. So that was the whole point of this right here. Oops. So yeah, do make sure that you get that down before moving on. Okay, but let's move on. So the next thing is we're going to go ahead into problem 7-96. We're going to be, again, we're still taking a look at the problem d of t equals 10t squared, but now we're going to go ahead and write an average velocity expression from t equals 4 to t equals 4 plus h instead of the 5. So step 1, we have to create our 2 coordinate points. The first one is easy because all we do is take this 4, plug it in right here. 4 squared, that's 16, times 10 is 160. Plug in 4, I got 160. Now the next point, I take 4 plus h, and I plug it in for t to get 10 parentheses 4 plus h squared. Perfect. Now I'm going to go ahead and follow the same steps I did before. The next step is I'm going to FOIL this out and or multiply this out and or use the box method. Whatever method works for you to multiply that out, please use. That's how I got 16 plus 8h plus h squared. The next thing, again, I'm going to do the same thing as I did before. I'm going to distribute the 10 in here to get this. And then once I have that, I'm going to do y2 minus y1 all over x2 minus x1. Whenever you have this setup like this, it's very nice because things will cancel out. 160 minus 160, that's 0. 4 minus 4, that's 0. And like before, we're going to pull out this common h right here, and then we'll be able to cancel out and have a very, very nice formula. I pulled out h. Look at what's remaining. Let's cancel out those h's. And we have 80 plus 10h. And this, again, is the units for this, because we're still talking about that car and its velocity is going to be feet per second. What's cool about it is we could plug in any value now for h, and we'll be able to find the average rate of change or the average velocity of the car for any h, when h is very small or when h is very big. Let's go ahead and talk about how we do this. Now, remember that in your quiz today, you're going to have to find the average velocity, but this time it's going to be between t equals 3 and then t equals 3 plus h. So you're just going to look back at these steps to help you out with that. Let's go ahead into the next one. So how do we use the expression right here that we just came up with, 80 plus 10h? Well, for the first one, and we're going to look at these calculations, right? Because we now created a much easier representation of the average rate of change, all we got to do is plug in h. So from 4 to 4.1 is our first one. Whoops, whoops, whoops. Okay, from 4 to 4.1 is our first one. So first we have right here the expression that we came up with here. And 4 minus 0.1 means our h is just 0.1. How we're moving horizontally is just 0.1. 10 times 0.1 is just 1. So from the average velocity of the car from 4 to 4.1 seconds is 81 feet per second. Notice I didn't have to create 2 points and then do all that h stuff like in video 1. I now have an easier equation to use. Now let's do the next one. When t equals 4 and then 4.01. So sorry about the order of this. It's going to project the steps and then I'll explain it. Sorry about that. So when t equals 4 to 4.01 seconds, again, all I got to do is plug in for what h is. So 4 minus 4.01 is just 0.01. That's my h, horizontal distance. 10 times 0.01 is just 0.1. 80 plus 1 is 80.1 feet per second. So great. So we're getting a closer and closer estimate of what is the car's actual velocity at t equals 4 seconds. But now notice that it's moving backwards now, so behind t. This is our next one. So when t equals 3.99, that's behind 4. Not behind t, my bad. It's behind 4 instead of to the right of 4. So the h in this instant is going to be, and let me again project the work first and then I'll explain it. It's going to be 3.99 minus 4, which is going to be negative 0.01. So notice that because 3.99 is behind the 4, the problem in question, it's going to be negative. So definitely pay attention to that. So it's going to be 10 times negative 0.01 is going to be negative 0.1. So we have 80 minus negative 0.1 is 79.9 feet per second. So from behind, from after 4.01, the average velocity is 80.1. Right before 4, it's 79.9 feet per second. So I'm like kind of making an estimate that I think at t equals 4 seconds, like when I'm driving on the road at t equals 4 seconds, I'm going about 80 feet per second. I feel like that's the instant velocity. Because look at these approximations, they're very close to 80. Now this is the one that's going to show up in your quiz that I'm going to help you start off, but you're going to have to finish. So this is going to show up in your quiz saying what is the average velocity from t equals 3.999 to t equals 4. All I did is I did 3.999 minus 4 to get my h. So then I got negative 0.001, and you're going to go ahead and finish this calculation on your own in your quiz. Lastly, before y'all head out, just wanted to show the visual. Again, I'm using this tool to kind of help represent what we're looking at. This again is still distance, and this is going to be my time. Remember 10t squared. But the point that we were just looking at was when the time was at 4 seconds. So I'm just going to adjust this just so that we have a visual of the car. I have to zoom out a little bit. There we go. Again, we're looking at the same point. And the first one I believe we did was when h was down here. Hard to see it because our animations are in the way. When h was 0.1. That means, there we go. It looks like the point's on top of t equals 4 seconds, but if we zoom in very, very close, we're going to see that there's actually 2 points, but they're very, very close to each other. Yeah, they must be very, very close for me to need to zoom in so much. Let's see, where's the other one? Go ahead and adjust this a bit. Oh, that's why. The x-axis step is looking really funny. Let's see, I know that we had about 80, so let's just make this, I don't know, negative 10, maybe 100. Sometimes adjusting this helps so that we can, shouldn't be 4 to 4, it should be like, I don't know, 0. There we go, I see it now, to 7. Yeah, so me zooming in, zooming out was kind of frustrating. Just use this toolbar right here if you want to, yeah. So the h, the distance, the horizontal distance from this point to this upper point right here was 0.1. And then you notice there are 2 points right there, and what we're basically doing is calculating the slope of that secant line and finding the average rate of change to determine an approximate velocity of the car between 4 seconds and 4.1 seconds. And then later on, right in the calculations, we went to making h 0.01. And when h is 0.01, the points look closer and closer. Again, they look virtually on top of each other, but they're not. They're just really, really close. And again, we have this horizontal distance. It's 0.01. It's very tiny. But it's still not exactly the car's exact speed at t equals 4 seconds, but it's going to be a very good approximation. Notice how I have 2 points here. If I was to do my slope formula between them, I will get 80.1 feet per second. But because I'm using this shortcut formula right here, I don't have to do that work. So again, this is a nice tool to kind of visually show you what's happening with this. Again, make sure that you review this video to refresh on those learning goals that we had at the beginning.